Before we get started, I'd just like to say that I understand this is a very long video. Don't expect you to watch all of it in one sitting, so I've put some timestamps in the description so you can jump around to different sections of the different topics that I will be covering. Thank you, and hopefully you get something useful out of this video. Hello, my name is Igor, and today I'm going to be walking through you guys a little bit of the content for VCE Further Maths Unit 3. Now, for the record, this is my first time doing anything like this, so bear with me if we hit a few speed humps or potholes along the way. If I do this more often, then hopefully I can smooth out some of these details, but enough about that. So we're going to be looking mostly at content relating to the first 6 chapters of the relevant textbook, and this is all going to be about data. So let's get started. Let's have a look at my notes up here. I've got some of the content topics from chapters 1 to 6. So let's make a start with chapter 1. Most of what I'm doing is going to be on this whiteboard here, but for some of it I will be switching to my computer to show you a little bit of what you can do on Excel, and I'll try to explain how you can do the same sort of thing on a CAS, which will obviously be very useful, especially for exam times. Alright, so chapter 1, one of the first things that they're talking about is categorical data versus numerical data. So numerical data is the easier one to remember. Numerical, numbers, this is the sort of data that you have numbers for. Things like someone's height, their weight, their age, maybe how much horsepower is in a car, how long someone takes to run a race, how much fuel a plane needs to make its journey from point A to point B, things like that. Those are all numbers. Categorical data, honestly, it's not the most common one that you'll see, especially in math, but nonetheless it is still important. And this is things that you can't obviously assign a number to. So probably the easiest example that I can think of is color. So if you think of the color of a car, maybe you have white cars, red cars, and blue cars. Or white, cars come in all different colors. So let's suppose we have white, pardon my handwriting, I haven't used a whiteboard in a long time, black, and let's say, just for good measure, let's say red. Obviously, in terms of cars, red cars go the fastest. Ah, camera can't see that. Well, that's a shame. Alright. Good job, me. And when I'm looking at my phone right now, it's all in a mirror image, so it looks like I'm writing backwards. But I assure you I'm not. So, let's suppose that in some neighborhood or a street or a block, let's say maybe there are, 100 white cars. Let's say there are maybe 80 black cars, and let's suppose that there are, 20 red cars. Now, how might you represent this data? Well, I think one of the most common ways that you can do for something like this is in a bar chart. So let's say you have your vertical axis here, and this will be number of cars. So let's divide that up. So let's say up here is 100, 80, 60, 40, 20, and down here, let's call that 0. And then here, I'm not going to put an arrow there because this isn't numerical data here, this is categorical. So let's call this W for white, B for black, and we'll call this R for red. So let's draw a dotted line here. So let's have bar comes up here. So this bar represents how many white cars are in the street or neighborhood. And let's say here, these are all going to be very wonky lines. I'm really doing this on quite the angle. Black, so let's say that's 80, and red, we said 20. So that, the bar representing the red cars would only come up this high. So you can tell from the numbers, but it's a bit easier to see with the graph that there are definitely the most number of, the color of car that is most common is white cars. Then black cars, there's a similar number, not quite as many, but still quite a few black cars. And red cars, Not so many red cars in comparison to the other two colours. Definitely not in comparison to the total number of cars. And that's 200 cars, 20 of them are red. It's 10% of the cars are red. Now, of course, this is a very simplified example. You probably wouldn't find exactly this sort of thing in real life, but nonetheless, it does show how you can represent categorical data. But moving on from categorical data, you have numerical data. And like I said earlier, these are, well, I don't know if I said this earlier, but this is probably the most common sort of data that you'll end up dealing with when you're, well, in this subject at least, and dare I say, the sorts of data you'd find in the real world most likely. Numerical data. So this is things like someone's height, maybe their age, how many children are in a family, things like that. You can easily put a number to this. So let's say that, we have a data set for number of children in a family. So let's say, first we just have a couple with no children, another one of them. We have some families with one child, some with two, and maybe a couple with three. And let's say that there's one family with 4 children, just for the sake of it. Yep, camera doesn't go that far. I'm gonna have to work on that. I'm gonna draw a line here. So I know roughly what the camera can see. Okay, there's a 4 down there, just for the record. So, there are 2 families that have no children. There are 4 families that have 1 child. There are 3 families that have 2 children. There are 2 families that have 3 families that have 2 children, 2 families that have 3 children, and there's 1 family that has 4 children. Again, sorry, camera didn't quite catch that. So, using a similar bar chart sort of method, let's say, so here will be 0, 1, 2, 3, 4. 1, 2, 3, 4. I'll put 0 there. This here is the number of children. Yeah, my writing's shocking. I'm going to have to work on that, guys. I'm sorry. So, there are 2 families that have 0 children. So, what we'll do, we'll also put 0, 1, 2, 3, and chuck a 4 on the end there. So, if 2 families have no children, on your axis of number of children, you look at the 0, and that bar will go up 2. So that's in line with the 2 there. There are 4 families that have 1 child, so this bar will go up to 4. And similarly, you have 3 families that have 2 children, and you have 2 families that have 3 children, and you have 1 family that has 4 children. Something like that. So again, number of children is along here, and this axis here is the number of families that have that number of children. So it's a bit of that's a very quick just pair of examples for categorical data and numerical data. And the last thing relating to chapter 1 that I want to talk about is the use of a log scale. Now, what is a log? Well, a log is really just a more compact way of expressing bigger numbers, in a sense. And this is especially, if you ever heard of the Richter scale, this is used to measure the strength of earthquakes. It's not a linear scale. So if you hear something like this earthquake had registered as a 6 on the Richter scale, if you consider that earthquake as a 6, and then you consider a different earthquake which registered as a 7, that earthquake registered as a 7 is actually 10 times stronger than what registered as a 6. And an 8 is 10 times stronger than what registered as a 7. And 9 is 10 times stronger than an 8. And a 10 is 10 times stronger than a 9. So log scales, they're not linear. So one of the most common uses of a log scale is actually for how loud things sound. And sound volume can be measured in this unit that we call decibels. So, as an example, let's say that, well, if you Google images search or just Google search how loud are certain objects, you'll find images like this all the time. Let's say we have a level of decibels. I don't normally draw these like that. Decibels. So let's say up here you have 150. Here, 140. Here is 130. Let's say 120. 110, 100, 90, 80, 70, and let's say 60. So 70, 80, and I'm just going to write sideways now. 90, 100, and 110. So, typical human speech, assuming that you're standing in front of the person you're talking to, that's usually between about 60 to 70 decibels. Alright? So, if you go 10 times louder than that, 80, you're at about busy traffic on a road. So if you're walking along a busy road and you have lots of cars going past you, that's about 80 decibels. Now, if you get a really loud truck or a motorcycle, again, 10 times louder. So it'll be 90 decibels. A car's horn, I guess it depends how close you are to it, but that's at about 110 decibels. And now, anything can be as loud as you like if you get really, really close to it. A whisper is all the way down at about 20 or maybe 30 decibels. But if your ear is right next to the person talking, you can still hear it just fine. And the biggest one on this picture I'm looking at, that 120 decibels, that's an aircraft taking off. So just because you talk at 60 and an aircraft takes off at 120, that is not twice as loud as 60. That's actually 10, 100, 1,000, 10,000, 100, 1,000, 10,000, 100,000, a million times. An aircraft taking off would be a million times louder than someone talking to you. Again, depending how far away you are from the aircraft. Most likely you'd be inside and the sound would be suppressed, or you'd be well away from it and the sound would be fairly quiet by the time it reaches you. But again, that's logarithmic scale, or an example of one. Now, if you were to represent this on a linear scale, so, now it doesn't make a lot of sense to have that there. If you call this decibels, but you have it being linear, if you were to plot this sort of thing here, you'd have talking would be there, traffic would be there, motorbikes would be there, horns would be maybe here, and then aircrafts would be around there. So that big range of volumes here on a linear scale, if you have a really big range, all the things down here are all very similar, and the differences between them are very difficult to see and not accurately shown on a linear scale. So that's one reason why we use log plots, or log scales rather. And that sounds a bit kind of going over your head as to, you still don't get it. Don't worry, we're going to come back to log plots later. They are not an intuitive thing necessarily. Although, for the record, apparently, and I dispute this a little bit, people can't distinguish volumes that are less than 3 decibels apart. And that's roughly doubling the volume. So in other words, if I played you something at 80 decibels and I played it again at 81 decibels, theoretically you wouldn't be able to tell the difference. You would only be able to tell the difference if I played you something at 80 decibels and then at 83 decibels. Now, if you're really paying attention, you can tell the difference, but it's very subtle. Even though 83 decibels is actually doubling the volume, because the way your ears work, just so it turns out that it's all kind of relative to something else. So, that's enough of an aside on log scales. Let me go back to my notes and have a look at what chapter 2 is talking about. Okay, dot plots and stem plots. Dot plots I'm okay with. Stem plots, personally I think, look, they're kind of useful, but to be honest, I'm not a big fan of them. We'll start with dot plots anyway. So, Now, let's use that example of dot plots are similar to bar charts, just by the way, but let's use that example again of how many children are in a family. So let's say that our data set is 0 kids in this family, 0 kids in that family, 0 there, 1, 1, 1, 1, 2 kids, 2 kids, 3 kids, let's say 4 kids, 4 kids, and 4 kids again. So, different data set, but number of children in a family. So let's say this here, your horizontal axis, is your number of children. And this here is your count. In other words, how many families have this number of children. So we'll have 0, 1, 2, 3, 4 as the number of children in the family. Now you may well get a question on an exam or a test where it says, given the data set, construct an appropriate dot plot. And this is sort of how you do it, although you would definitely be using a ruler for this. Because if you did this in the test, boy, I personally I might take at least 1 mark off for just sloppiness. But I'm proving a point. And I'm using one hand and I'm getting off track. Okay, count. So let's say here is 1, 2, 3, 4. Do I have any more than 4? No. Okay. So 1, 2. Actually, you wouldn't actually need this. I'm thinking of bar charts again. So what I'll do, I'll actually get rid of that. Because you shouldn't need to label that axis. But we have 1, 2, 3 families that have 0 children. So, 1, 2, 3 dots. We have 1, 2, 3, 4 families with 1 child. 1, 2, 3, 4 dots. You want to try to keep the dots roughly in line with each other. So you don't want to have a column of 4 dots being the same height as a column of 2 dots. Now we have 2 families that have 2 children, so we'll put 2 dots in this section. We also have 1 family with 3 children and 3 families with 4 children. So with that data set there, this is how you might represent that on a dot plot. Similarly, if I gave you the dot plot, but not the data set, and I asked you something like, how many families have only 1 child in it, you might look at this and say, okay, there's the group of families with 1 child. There are 1, 2, 3, 4 dots in that section. Therefore, there are 4 families that have 1 child in them. Making sense? I can't actually hear your answer, so that was a rhetorical question. Probably shouldn't do that too often. But let's move along to stem plots. Now, it took me a good solid, maybe like a solid 10 minutes looking at a stem plot trying to figure out what on earth it was trying to tell me. But, so I'm going to try to do my best to actually explain what these silly looking things in your textbook are. So, stem plots have what's called a stem and a leaf. Why are they called stems and leaves? Well, think about trees. That's the only answer I can actually give you. Yeah, I got to work on these straight lines. Maybe I should sit behind the camera and draw next time. Anyway, so we'll start with, I'll give you a data set. So let's suppose we have, I'll write these numbers in order just to make it a little easier to see. So let's say we have, again, what's the starter representing? I don't know. But we'll just put some numbers in. So let's say we have 7, 8, 11, 15, 19, 20, 23, 23, 31, 36, and 47. Okay, now, each one of these numbers is obviously a number in our data set, and each combination of stem and leaf in our stem and leaf plot will correlate to one of these numbers. So, this number 7, there's only 1 digit in it. 7. It's not a 1 and a 7, that would be 17. So our stem, because there's no number in front of it there, we'll put 0 for the stem and 7 for the leaf. We'll put a comma there. Next number is an 8, not 18, just 8, so it's still in the 0 stem. Now, the next number we have is 11. First digit in 11 is a 1, so it will be in the stem of the 1, and a 1 for the leaf. Next one is 15, so I'll put a 5 in the leaf. And the next one is 19, so we have that, and I'll fill out the rest of this just for completion's sake. So 20, 23, 23 again, so we write the 3 twice here, because this is 2 separate numbers. It's the same value that appears twice, but they are 2 different numbers. I hope that makes sense. I'm going to get myself in a circular loop if I think about it too hard. And, of course, we have 31, 36, and 47. Now, usually, they would give you, well, maybe not usually, but if someone gives you something like this, and they don't give you any context to it, this would tell you that your numbers in this data set are 7, 8, 11, 15, and so on. So 7, 8, 11, 15, 19, 20, 23, 23 again, 31, 36, and 47. Now, it may be that perhaps these stems could represent... drop my pen. Perhaps these stems represent tens. Now, what do I mean by that? Perhaps they could represent millions of dollars. I'm just going to put a tens here. So the leaf here, let's say, so if that's 0, so I'll just keep it really simple for this one. So let's say, I hope you wouldn't see this, but if you did, let's say 1, and let's say 43, that's a 4, and 98. So if that's in tens, so there's 0 there, so this 19 and 15, that's still just 19, 15. Because this 1 is now the tens, that's actually 100, and this is 43, so that'll be 143 and 198. Now, any question you get should specify what the stem is. If it doesn't specify, just assume that it's like it was the example we had earlier. But just for the record, so you know, the stem might be something a little bit different, especially if it's a question about finances. That stem could be thousands of dollars. And then you might have some other numbers there. So you might have, so if that was 1, that could be, let's say you had 300, that would be $1,300. But again, read the question carefully. The stem might not be exactly as it appears, but that's basically what stem and leaf plots are. Personally, I think having numbers written as they actually are is a little more useful. It doesn't mean, and especially if you try to put it into a CAS or a computer of any sort, a little more useful that way. Okay, so that's dot plots and stem plots. Now, we have we're going to talk about the median, the range, quartiles and the inter-quartile range, as well as determining outliers. So, I'm only going to make up one data set for this, and from memory, I think it's easiest if we have 11 data points. So, let's come up with some numbers. So let's suppose we have 5, 6, 6, 8, 14, how many is that? 1, 2, 3, 4, 5, 16, 6, oops, there goes my whiteboard. Good job, me. 17, hang on, 1, 2, 3, 4, 5, 6, 7, 22, that's 8, 25, that's 9, 31, no, right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and let's say 48. Okay, so we have 11 numbers written in a not very straight line at all. Now, how many things did I say? I think there were 3, maybe 4 things I specified, but the first one I'm talking about, sorry if you got the light reflecting there, hope you can see all the numbers. First one we're going to look at is the median. Now, you may have heard of 3 different types of averages. You have the mean average, the median, and the mode. The mean average, that is when you add all the numbers together and you divide it by the total number of numbers you added together. So if you added all these numbers together, there's 11 numbers, and divided that answer by 11, you would get what's called the mean average. The median is the number in the middle of this data set. Now I've written this in order to make the middle much easier to find. And the mode is the most frequent or most reoccurring value that is in the data set. So in this case, 6 is the only value that recurs, so 6 would be the mode of this data set. But let's talk about the median first. So there are 11 data points in this data set. What is half of 11? 5, 6, well, if you chuck into your calculator, you're going to get 5.5. So you would expect, so you might think, okay, well, it should be, the 5 1/5 value of this data set. That doesn't quite make a lot of sense, but the safest way to do this is quite simply to count from that end and that end. So you have 48 and 5, 631, 625, 822, 14, 17, and then 16 is your number in the middle, right? So 16, this number here, that will be our median. Or, now median's in the middle. Now, hopefully this isn't the first time you're hearing the concept of quartiles, but right now we've divided this data set into 2 halves. So you have your left half and your right half. Well, I guess the first half and the second half would be a better way to describe it. But with quartiles, what's that doing? That's dividing your data set into quarters. So, the median being in the middle would also be, you could also call it the second quartile. You'll have your first quartile, your first quartile, your second quartile, and your third quartile. Is there a fourth quartile? Funnily enough, no, there is not. You think quartile, there's 4 of them, and there's actually only 3. But you are dividing your data set into 4 parts. So, that's your median, or your second quartile. To find your first quartile, let's look at this first half. And we'll do the same thing we did for the median. Let's start from the outside. 5 and 14, 6 and 8. This 6 here, that is your first quartile. And same thing here. 17 and 48, 22 and 31, 25. So, we'll call this Q1. Call this one Q2. This is also your median, by the way. And we'll call this one Q3. First quartile, 6. Second quartile, 16. Third quartile, 25. Now, interquartile range. That's the next thing I'm going to be talking about. Your interquartile... actually, should I do range first or interquartile range? No, I'll do the range first. Okay. So, your median, first quartile, third quartile. Your median is also your second quartile. Now let's talk about the range. If you think about, well, in the case of singing, for example, a singer's range would be a measure of what is the lowest note they can hit and what is the highest note they can hit. The further apart those 2 notes are, the bigger the singer's range. Another example of use of the word range, not the most mathematical necessarily, but especially if you hear talk about electric cars, you'll hear a lot of talk about what is the vehicle's range. That is, how far can the vehicle travel on a full charge of batteries? Or in a more common petrol car, or diesel car, or whatever, how far can it travel on a full tank? That's the car's range. Or in other words, how far from its start to its end can it get on that full tank? So in terms of data sets, when you talk about range, it's what is the difference between the biggest value and the smallest value. In this case, we have 48 and 5. So your range, which I'm just going to call R here, but again, if this is an exam, I'd write the word range. That will be equal to 48 minus 5. It's your biggest value minus your smallest value. So R will be equal to 43. I really hope I got that right. Yes, I did. So your range is going to be, so if the question was, what is the range of this data set? Your answer would be, range is equal to 43. Pretty straightforward. The interquartile range, sorry, I'll say it slower. I talk a bit fast sometimes, sorry. The interquartile range is similar to the range in a sense of you're subtracting your biggest value from your smallest value. But we're going to subtract the biggest quartile from the smallest quartile. So in this case, that's, well, sorry, in the case of interquartile range, that is always going to be quartile 3 minus quartile 1. So interquartile range, which is commonly abbreviated to IQR. I'm going to change how I'm sitting. Oh, much better. No, maybe not. Interquartile range is equal to Q3 minus Q1. In this case, the values that we're going to use, we know that quartile 3 is equal to 25 and quartile 1 is equal to 6. So your interquartile range is going to be equal to 19. That's all there is to interquartile range. Pretty straightforward. Well, I think it's straightforward, but finding your quartiles can be a little bit challenging in some cases. So, range is your largest value minus your smallest value. Interquartile range is your quartile 3 value minus your quartile 1 value. What have I got next to talk about? Determining outliers. Now, you can see that the numbers, they start small and they get a little bigger. It's a bit of a jump there, pretty steady, jump there, jump there. 48 kind of stands out from the data set. It's pretty far away from all the other numbers. So, to determine, in the mathematical sense, is this an outlier? What we do is we look at quartile 3. So that's 25. So, to determine, I'll erase the range a bit. So, outliers. Outliers. I believe I spelt that right. I did not do too well in high school English, for the record. Now, so you start. So let's say we want to find the outlier on this side. You can have outliers on the lower side as well. But in this case, let's look first at on the higher side. So we'll start with quartile 3. And then we are going to add, because remember, this number is bigger, so we want to look further up, so we want to make the number bigger, so we're going to add to it. 1.5, the interquartile range. Now luckily, we already calculated what the interquartile range is. It's 19. So, substituting Q3 and IQR into this equation, this is actually an expression, but if you put those values in, Q3, 25, plus 1.5 times 19, so you end up with 25 plus, now what's 1.5 times 19? 19 is pretty close to 20. 1.5 times 20 will be 30. The 1.5 times 19, let me make sure I'm getting this right. 9, 4.5. Oh boy. 28.5. Correct me if I'm wrong. I don't have a calculator, so I can't actually cheat to find this out. But if you have a calculator, you should be using it, because you will not have an excuse for getting things like that wrong. Okay, so then if we add these together, well, you'll have a 0.5 at the end. 5 plus 8 is 13, carry the 1, 53.5. So, if the biggest value you had here was equal to or greater than 53.5, then it would be an outlier, and you could get rid of it, or you could ignore it in any subsequent analysis. So if, for example, this 48 was actually 55, then that would be an outlier, and we could get rid of it. But for now, let's keep that as 48. So it's almost an outlier, but it doesn't quite fit the definition of what an outlier is. Now, let's just remember, inter-quartile range is 19. I'm going to show you the other way for if you want to find if you have an outlier on that side. So remember, inter-quartile range equals 19. Now, this is to see if you have an outlier on this side of the dataset. To find if you have an outlier on that side of the dataset, it's a very similar equation. Instead of Q3, we start with Q1. Kind of makes sense with going there. Instead of adding, we're going to subtract because we want to see if numbers are much smaller than what Q1 is. So minus, but this bit stays the same. Minus 1.5 times IQR. So if we put in the values that we know for these, they're not variables, we know what they are, but Q1, that's 6 minus 1.5 times 19, that equals 6 minus 28.5, and if I do it the other way, if I add 28.5 minus 6 would be there should be a negative 22.5. Now just for the record, what I was talking about, 6 minus 28.5, in my head that's kind of hard to do. But 28.5 minus 6, that's a bit easier. So I was doing that in my head and just putting a negative sign on the front to make that, to make my answer applicable to this. So, do we have any values here that are less than or equal to this value here? And the answer is no. The lowest value we have is 5, and that is definitely well above negative 22.5. So, we've talked about your median, finding your quartiles, the interquartile range, that's subtracted by that, your range, your biggest value subtracted by your smallest value, and how to find outliers on both sides. Now, my phone didn't move, still okay. Next thing to talk about. Now, the textbook that I've been looking at mentions a 5-number summary. I think the only other number that I haven't talked about is standard deviation. And I think that's what they want in the 5-number summary, but honestly, we'll come to standard deviation later, but to preempt what's going to happen, standard deviation is a number that tells you what your spread of your values are. So if all your values are very spread out, you'll have a high standard deviation. But if they're all really close together, then you have a low standard deviation. So if this is like 5, 6, 6, 6, 7, 7, 7, 7, 8, 9, 10, you'd have a very small standard deviation, maybe 1 or 2. But here you might have a standard deviation for this sort of data set of maybe 6, something like that. I don't know. I could be completely wrong with those guesses, but the point is, the more spread out the values of your data set, the bigger your standard deviation will be. Now, let's get on to box plots. I am going to keep this data set up here. Now, do you remember what the outlier values we determined were? From memory, it was 53.5 and negative 22.5. I'm just putting those. Now remember, this is not part of the data set. It's just so I can write it there so I don't forget what they are. And I could be wrong about that anyway. But we'll say these are our outlier things. This number is Q3 plus 1.5 times your interquartile range. That's Q1 minus 1.5 times your interquartile range. So, no, not box plots, not stem and leaf plots. We're talking about box plots. Yes, box plots, not dot plots, box plots. So, let's say we have a number line, everyone's favorite friend. Let's say here is 0, and let's say here is 50. And I'll make it go a little further out those ways. We'll put some arrows there, because the number line is in principle infinite. Now, what is our median? Well, our median is also Q2, 16. So this is 50, 0, 25 might be somewhere here. 16, let's say it's around there. So say that's 16, and we'll draw a line for that there. Q1 is at 6, so if that's 16, yeah, I got the scale really wrong on this one. We'll call that 6, draw a line up there. Q3 is at 25, so I'll put that there. Now, so I'll put 25 in there. Your box in this box plot is made up from Q1, Q2, Q3. Now I drew a bunch of lines here, but I'm going to add some more lines to make a box. I gotta say, here you have a standard square. Well, slow down there, Einstein. But if you add a few more lines, you have a three-dimensional cube. Amazing. Sorry, I'm a big fan of The Simpsons, and I'm reminded of the Treehouse of Horror where Homer gets trapped into the 3D world. Did anyone see that movie, Tron? I've not seen Tron, for the record. Anyway, let's get back to math. Sorry, I'll probably have a few more of these silly references and jokes that aren't actually funny to people who aren't me. Okay, Q1, Q2, Q3, this is your box. Now, box plots have what's called the box and the whiskers. What is the smallest value of our data set? It is 5. So, we'll call that 5. And we'll have a whisker that extends from Q1 to your minimum value, which in this case is 5. What is your maximum value? Your maximum value in this data set is 48. So that would be somewhere around here. So, you would draw a whisker from your maximum value all the way to quartile 3. And this here would be your box plot of this data set. Now, if, this is the big if, because remember, we're assuming that this box plot is a representation of this data set. Let's imagine for a moment that we change the data set. Let's suppose that instead of 48 being the biggest value, let's say it's 60. So 60 might be somewhere up here on the number line. Now, we've already calculated the quartiles. Even if this is 60, the quartiles are not changed. Therefore, your interquartile range has not changed. That also means that your method for determining if there are any outliers has not changed. So negative 22.5, 53.5 are still your cutoff values for does this data set have an outlier? If 60 is your biggest value, you would determine that yes, this is in fact an outlier because 60 is greater than 53.5. So what you would do then, you would put an X here to say this value is an outlier and has been discarded in this box plot. And instead, your next biggest value would be 31. So let's say 31 is there. Put a dot. That would be your whisker. And yes, they are actually called whiskers. That's what the book says. People who write textbooks on math, people who are good at math, they are strange people, but they are brilliant people. And I am not, I might sound slightly smart, but believe me, there are some very smart people who are very good at math. Now, if you look at this box plot, you can see this outlier, just visually, this data point here is way away from the rest of the data of the box plot. And that's what you would expect of an outlier. You wouldn't expect an outlier to necessarily, well, it could be close to there. I mean, if this 31 was instead, let's say 45, then your whisker might extend all the way out to there. And you could have an outlier that's quite close to it. But at least in this case, it's very clear that this is an outlier from the rest of your data set. But in principle, you could have a whisker that goes all the way up to this point. I mean, if that 31 was a 53, you wouldn't be able to discard it from your data set. So if you did have an outlier in your data set, and you were asked to find in the interquartile range, determine are there any outliers? Yes, there is an outlier. Now draw the box plot. This is what you would be drawing. So you have your box here, which is a combination of quartile 1, 2, and 3. Your whiskers, which extend all the way out to your minimum and your maximum value. And you can put a little X where the outlier that you have discarded came from. Or if, let's say you're in an exam and they give you a number line, and let's say the number line only goes up to there. You haven't got it, and there's no paper in your test to put an outlier in there. Just don't put your outlier in there. You've pointed out that it's an outlier and has been discarded from the data set, so no need to include it. Now, let us put... So that is box plots. That's the next point I'm meant to be talking about. Box plot, use of box plot to describe and compare distributions. Okay. Now, when you look at a box plot like this, distance from there to there looks pretty straightforward. So it's not particularly heavily skewed one way or the other. But this whisker here is a lot longer than that whisker there. So you could say that there is a skew to the higher values here, or it's positively skewed. Similarly, if you had a box plot that looked like this, nice and symmetrical, hasn't been skewed. If you had a box plot that looked like this, negatively skewed. Or if you had a box plot that looked like that, positively skewed. So looking at these box plots, you can tell that so quartile 1, 2, and 3, it'll be a pretty even distribution. Here you have a lot more numbers. Sorry, the earlier numbers in your data set have a very big range. So that, let's say that's 1, 5, 20, 21, 22, 23, 26, 28, 30. So you have a much bigger range in your earlier section. And similarly, you have a much bigger range in your larger values here. So that's, let's say, 50, 45, 40, 30, 27, 26, 23. Something like that. Now, one more thing I want to mention in terms of finding the median and consequently the quartiles as well. Let's say this is your data set. And let's see if I can get rid of these circles. Not bad, not bad. So, now we only have 10 data points in our data set. That's okay, but let's say that we use the same method to find the median. So 5 and 31, 6 and 25, 6, 22, 8, 17, 4, 16, and there's our number in the middle. So we're stuck between 4 and 16. Check your textbooks on this one. Some people might say take the smaller number as your median. Some people might say take the bigger number. I think the better representation is to take an average of the two numbers. So remember, mean average is where you add the numbers together and divide them by how many numbers you added together. So 14 and 16, add them together. Two numbers divided by 2. So that's 30 divided by 2, which you may have guessed is 15. So 15 is your median, or alternatively you can call it quartile 2. Now, quartile 1 and quartile 3, in this case, will still be the same. But if you have different amount of data points, you may have to do a similar thing in terms of averaging the two data points that are in the middle of your data set. So just write Q1 and Q3. Okay. So that's a little bit about box plots, interquartile range, determining outliers. Let's see, looking at my notes. Use box plots to describe and compare distributions. Yep. Center and spread of symmetric distributions. And normal distributions. Okay. Alright. The normal distribution. This is actually what your study scores, or how your study scores, it's a little bit. It's a part in how your study scores for all your VCE units are determined. And it's more formally called a normal distribution. I believe it's the same thing as a Gaussian. Don't quote me on that. I should know that though, but hey, no one's quizzed me on it in a long time. But it's more colloquially, or more commonly referred to, I can do better than that. It's more commonly referred to as the bell curve. Looks something like that. Because it looks kind of like a bell. I mean, maybe tip your head upside down to see the bell. Sometimes mathematicians can be creative in the shapes they see. Anyway, or I could just be better at drawing stuff. Now, your bell curve is, theoretically, well, mathematically, your bell curve is symmetrical. So everything on the left half should be the same as what's on the right half. Same shape, at least. The total area under this bell curve represents 100% of the data that you're concerned with. Now, you remember how I mentioned standard deviation? That's a measure of spread. So if you have a bell curve, let's say we have bell curve like this, and one like this. This here, now I'm using an O, or it's a sigma, is the Greek letter. That's a symbol you use for standard deviation. So here, your standard deviation, I can do better than that, is small because all your data is clustered together really closely. Here, your standard deviation is large. Now, in terms of curves and spread, I guess given the fact of the year we live in and the obvious pandemic that's making you all learn from home right now, you may have heard talk of flattening the curve. It's kind of what this is. So, if this, talking about the case, this were the number of COVID-19 cases or infections, you would, and this here is time, you want this one rather than this one. Because if this happens, you're going to have, let's say, up here, let's say that's for one city, that could be 100,000 people who simultaneously have the coronavirus. Here, that might only be 5,000 people. If I were a hospital, I would much rather have only 5,000 patients rushing to my doors at once than 100,000 patients rushing through my door. This sort of distribution, which explains why preventative measures for spreading viruses are so important. And presumably, if everyone who gets the virus, let's say they survive and they're immune to it, eventually there won't be enough people that can get the virus left. So that will happen. So you might get the same total number of infections, but spreading it over a longer time period will allow hospitals to better handle what's the sudden influx of patients. Now again, standard deviation. This is the small standard deviation, this is the large standard deviation. But for this bell curve, this normal distribution, if you are, what's the best way to explain standard deviation? We use the study scores. So let's say in the middle, right? So if the minimum study score you can get, let's say it's 0, and the max you can get is 50, you might think that in the middle here, that the average study score is 25. And you'd be wrong, I think. At least I think that's what it was in my day. the average study score is actually 30. Maybe the minimum isn't 0. I don't know, to be honest. But to keep things nice and symmetrical and say the max is 50 and the minimum is 0, let's say the middle here is 25. Now, there are going to be a lot of people who get a 25. It's actually a 30 for VC, but let's say it's a 25. And there are a very small number of people who can get a 50. Fun fact, for Latin, there are not enough students in the States, or perhaps even, I don't know how, at least when I was doing it in high school years ago, there are not enough students in the state for there to be a student to get a 50 study score for Latin. Actually, I think it's at 55 technically. But, yeah, let's say for English, I mean, everyone's got to do, is it? I think English should still be the most, have the largest number of students in it. Let's say, you get maybe 10,000 students get a 25. It's probably, let's say 1,000 students get a 25. Maybe only 10 students can get a 50. Point is, there's a lot less people getting 50s than there are people getting 25s. Now, if you move one standard deviation above and one standard deviation below from the mean or the median, we'll say the median because it's in the middle, but it's also the mean because it's a symmetric distribution. So this will be 1 sigma, we'll make that positive, make that negative. This would encompass, that is 68% of all the study scores that will be given out. If you were to move 2 standard deviations away, plus or minus 2 sigma, that would be equal to 95, 98, 97, what's my notes say? 95%. So in this data, so let's say this will be a study score. So let's say you have a standard deviation of it's not quite 10. Let's say I'm trying to think of let's say it's 8. Okay, so 25 plus 8 would be 33. Minus 8 would be 17. So between 17 and 33, you would have 68% of all the students would have a score within that range. So let's say this is, what did I say? 33, 17, add another 8, 41, and 9. 95% of all students would have a study score between 9 and 41. And then if you were to do another standard deviation, let's do this. So this will be 3 sigma. That would be 99.7%. And if we add 8 again, that would be 49 and 1. Now, of course, for a model like this, we know that you can't get a score below 0 and you can't get a score above 50. This distribution technically goes on forever. Technically. In this practical example, it does not. The scores don't go above 50. For languages, I believe they go to 55. That's beside the point. So, to recap, plus or minus 1 standard deviation, plus or minus 2 standard deviations, and plus or minus 3 standard deviations. That will encompass, for 1 standard deviation, 68% of the total data points, or values. For 2 standard deviations, that is 95%, and for 3 standard deviations, that is 99.7%. Now, suppose, for a moment, we have another normal distribution, and let's say you want to know let's say the question is something along the lines of, there, what percentage of people will have a study score between the median and one standard deviation above the median? So that there is one standard deviation. So we're looking at, shouldn't have written that there. We're looking at this area here. How much of that graph is encompassed by this shaded area? Now we know that if they asked about plus or minus from the median, this would be 68%. But keep in mind, this is symmetrical. So, if you cut that in half, 68%, you should have half of 68% on the left side and the other half should be on the right side. So from the median to the right side, that's right, from the median, and if you add one standard deviation, that should be half of that. So that should equal half times 68%, which will give you 34%. Now, perhaps you will want to know, okay, what about, let's say, I'm not sure how you'd word this, but let's say you have another distribution, here's your median, here's one standard deviation, here's your second standard deviation. You want to know that area. A little bit more tricky. Now, consider that. So this is between 1 and 2 standard deviations. Now we know that plus or minus 2 standard deviations is 95%. We also know that the first plus or minus first standard deviation is 68%. So, if we consider just this first area, we know that's going to be 68%. This area here, plus that area there, should add up to 95%. So if we do, I'm going to work up here. So if we do 95 minus 68, that'll be an 8, carry the 1. So that should be 2. 27%. So these areas here and here should account for 27% of the total area under this curve. Now if you only care about one side of this, remember it's symmetrical. So that should be equal in size to that. So then 27 divided by 2 will equal 13.5%. Sorry, 27%. That should be a percent there. Now, I realize this is all getting kind of small and crammed in there, but the most important thing, if you're getting a bit lost with this stuff, go back, watch it step by step. But the most important thing, plus or minus 1 standard deviation, 68%, 2 standard deviations, 95%, 3 standard deviations is 97%. And that is a rough graphical representation of what that looks like on a bell curve. Also, don't spread around COVID-19. That will overwhelm hospitals. Funnily enough, stay at home, take a holiday. You're saving everyone by not doing anything. Very counterintuitive message to me. But the show must go on, and you kids are all stuck doing school on computers and not in classrooms. Well, maybe not all of you, but you get the point. And now you're stuck listening to some random dude on the internet trying to teach you math for some reason. Okay, that's all of chapter 2 for now. I realize this video is going for quite a long time. Feel free to take a break. Maybe I'll upload this in parts. But let's move on to chapter 3. Chapter 3, first thing we're talking about is the response and explanatory variables. So this is all about, well, it's all about plotting data sets and trying to make sense of them to find how one variable relates to another variable. So, okay. Let's suppose you have a car or a motorbike. And let's say it's got some power. The engine has some power. You can measure it in kilowatts, horsepower. Doesn't matter too much. I'm not going to give units for this. And let's say a top speed. Let's suppose it's in kilometers per hour. Now, let's say you have let's suppose that's kilowatts. Let's suppose that's in kilometers per hour. I'm making these numbers up, so they're probably not going to be remotely accurate to any actual cars. Anyway, so let's say we have a car's got a power of 50. That might actually just be a moped or a bunch of really strong dudes on one really big bike. Let's say it's got a top speed of 40. Let's say we have a car with a power of 100. Let's say it's got a top speed of 80. Alright, let's say we have a power of 150. 200, 250, 300, and I'll put 350 in there as well. 350. Marvelous handwriting I've got. Alright, let's say, oops, sorry. Let me make that a little more clear. So let's suppose top speed here for 150 is 100. Power is 200. Let's say I have a top speed of 120. Then let's say 130. 140, and 150. Now, if you're building a car, you'd probably know what power output it can give you. So that would be your explanatory variable. That's what you know to start with. Or alternatively, your explanatory variable might also be called your independent variable. So let's call this, this one's power. And let's call your y-axis, this is your response variable, or your dependent variable. Your top speed depends on what your power is. So this is your explanatory, this is your response, or this is your independent, this is your dependent. This one depends on that. So we'll call this one top speed. I'm going to be lazy and just write speed. So let's say you have your powers of 50, 100, 150. I didn't do that too well. I run out of room. Alright, 50, 100, 150, 200, 250, 300, 350. And let's say we have 20, 40, 60, 80, 100, 120, 140, 160. Anyway, this would be much easier to show on a computer, but so you can sort of get a very rough idea of what we're talking about. Again, explanatory variable, response variable. So 50 has a power speed of 40. So this is all in Microsoft Excel. This is all under what you would call a scatter plot. So we're not going to be drawing lines, not yet anyway. We are just going to be putting points on a plot to represent this data here. So if you have a power of 50, 50 along here, 50, 100, and so on, and your top speed is on your y-axis. So 50 is your power, 40 is your top speed. 100 goes up to 80, then next one is hundreds, then 120, then 130, then 140, then 150. So if you were to draw a straight, now you won't get a perfect straight line through this, but if you were to, you want to get your straight line as close as you can to as many dots as possible. And that's a pretty pathetic straight line. But anyway, this dog doesn't fit a straight line particularly well. It would fit a different curve better. We're going to get into that a fair bit later into this. But for now, we'll just leave it at that. So, again, explanatory variable, response variable, x value, y value. Always try to put your x value as the thing you know and the y value as the thing that you're trying to figure out. In this case, you know what the power of your car is, you then would measure what its top speed is by presumably taking it onto a racetrack or a runway or something like that. I can only imagine having a giant runway and this little moped with a tiny Vespa-sounding engine on it trying to get a top speed and just getting absolutely overtaken by everything. But that aside, let's move on to, I'll leave that there just in case it's useful for something else. Next topic in chapter 3, associations between two numerical variables. Okay, now, actually I will get rid of this data here. I'm just going to use a generic x and y for this case. But, oh, there goes the lid of the pen. There we go. Let's say that here is your x-axis, and here is your y-axis. We're not going to draw a line. We're just going to draw a bunch of dots. Dot here, dot here, dot there, 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 dot there, dot there, dot there. Draw that a bit better. Dot there, dot there, dot there. Maybe one here, one there, and one there. Let's put one here as well. Why not there? If you saw this, would you think that x and y have a linear relationship? I would think not. There is no obvious one straight line you could draw through there where you could say, yep, that line is a good representation of the data we've got. If you had x, y, dot here, dot there, dot there, dot there, you might say, okay, you could draw a straight line that would either go through or go very close to all those points. Like that. There is no line you could draw through here that would do that. Okay? So the correlation between x and y here is very weak. If anything, you can actually get data sets that are perfectly random, which have no correlation, or where x has no correlation to y. Usually, if you were to do random data sets, you'd expect a tiny bit of correlation, but it would be so small that it would be the logical conclusion is that there is no correlation. If you get exactly no correlation, it's probably because someone deliberately gave you, or doctored the data to have no correlation. But anyway, got rid of the x-axis. Better draw that back in. Here we go. Now, I drew some dots pointing there. If I gave you a bunch of dots doing that, you might think, okay, I can draw a straight line through those dots. Those dots match pretty close to it, so you say that's a, well, because that has a negative gradient, you'd say that would have a negative correlation. Now, negative doesn't mean it's a bad correlation, it just means that the correlation has a negative gradient. But it is a strong correlation. That line very closely goes along our data points. Now, let's suppose we have instead maybe dot here, dot there, data point here, data point there. If I say dots and data points, I'm talking about the same thing. Now, here, I'd still call that a strong correlation. It's still clearly trying to follow a line, but if I try to draw a line through this, I probably could have done better than that, it won't go through every data point. There is some error in where these data points are too far away from that line. Now I'm going to give you another example where I can highlight this a little better. Let's suppose we have data point here, data point there, data point here, data point here, data point here, and why not, let's put one here. Let's say I try to draw a line through this. Now my objective is to get the line to go through, to be as close to as many dots as possible. So maybe, hang on, that's not a straight line. That stopped me before, but I can do better. So let's say maybe it's like that. So the line doesn't go through any points, but you're looking at that data. There is a correlation as it gets more along the x-axis, it goes more up the y-axis. So there is a correlation, but it's not. It's clearly a positive correlation, but it's not a particularly strong correlation. There's still a fair bit of error. Sorry. And the way that you quantify error, okay, let me rephrase that. The way you assign a numerical value to error is what we call residuals. So you would consider so let's say you have a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, and so on. So that distance between that point and the line might be a residual of 1. Distance between this point and the line might be a residual of 2. Here, maybe a residual of 0.1. This residual could be maybe 4 or 5. Here, pretty small residual, probably less than 1. Here, about 1 or 2 maybe. So the idea is you want to make a line that is angled just the right way and shifted up and down just right, so that when you add all these together, the sum is as small as possible. Or what's more commonly done, let's say that's a 1, let's say that's a 2, call that a 5, we'll call that a 1, and let's call that a 2. Again, not the scale, but if you were then to have a table of residuals and your x values, okay, let's say it's, I know I didn't draw my x values at 1, 2, and 3, but let's just say it's 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, 6. And your residuals here are 1, 2, 2, 5, 1, and 2. Usually, what computers or your calculator will do when they try to give you the best line possible, they will consider your errors here, or your residuals, and they will square them. So 1 squared is 2, 2 squared is 4, 4, 25, 1, and 4. And then it will try to get a total, which I have called tot here, 1, 5, 9, 34, 35, 39. So your computer or your CAS is going to do some math to work out what line can I put in to make this number here, the total of all these residuals squared, as small as possible. So what that means is that if you have one really big error here, it's going to make a bigger effort to reduce that error than the smaller errors. Now, you can say 1, 2, 2, and 5. Okay, 1, 2, 2, and 5, they're kind of close together, but 1, 4, 4, and 25, that 25 is making the largest contribution to that 39 there. So you care more about that 5 than you do about that 2, in terms of if you're trying to make the error as small as possible. Now, that's a little bit beyond what you need to worry about, but when they talk about finding lines of best fit or with the method of least squares, this is the sort of thing that they're talking about. Most of the number crunching to make this as small as possible is done behind the scenes on a computer or a calculator. But just so you know, residual or method of least squares, this is the sort of thing that it's talking about. And again, this is a little bit beyond what you need to do yourself in the course, but just so you have a little bit of an idea of what they're talking about. Now, what have we got? Okay, calculating the correlation coefficient. Now we haven't got to this yet, but when you start trying to plot graphs on your CAS, you can also make it, so let's say we have this data set here. I'll give you a new data set, or give you a new data set, similar. So let's say point here, point there, point here, point here, point here, and point here. Let's say you try to, your graph says that's the line which best fits this data. Your CAS, or Excel, will give you an equation for this line, and it will usually be something like y equals, I don't know, let's say 2.31x plus 1.287. Something like that. I made up those numbers, just for the record. But that's very similar to what you've seen for many years now of y equals mx plus c. I'm sure you're familiar with this. But what your graph will also give you, it will usually give you a little thing, sorry, it won't give you, you'll tell it you want your equation in a format like that. But you can also get this little thing called r squared, and here it might equal, let's say, 0.8521. I made that number up. But what this r squared thing is, and this is not your correlation, wait, what did I say? Correlation coefficient? Where are my notes? Correlation coefficient, okay. R squared is actually your coefficient of determination. Coefficient of determination. All right. Now, r squared is that. Alternatively, you have this thing which we call r. That is your correlation. No, I spelled that wrong. There's a double letter in there somewhere. Coefficient. Like I said, spelling ain't my strong suit. Now, r squared and r are very similar. They both describe, in a sense, how well does your data fit the line you've drawn. Or, alternatively, it also says how well does your model describe what your y value will be based on what your x value will be. Because if you get an equation like this, you can put in whatever x value you want, and you can get a y value out of it. It might not be a sensible thing to do in some cases, but you can do it, mathematically at least. So let's say, the biggest x value here is, let's say it's 8. You can put an x value of 10 into that equation, and you'll get a y value answer out of it. But your coefficient of determination, or your r squared, that will tell you how well does this equation, or this line, explain the data that you've got here, or how well does it explain the relationship between your x values and your y values, or how well does your equation predict what your y values will be based on what your x values are. Your r value, well, as you can see, you have r squared and r, and as you might expect, or maybe you didn't think about this at all, like me, r is actually equal to the root of r squared. Or alternatively, if you take r and you square it, you'll get r squared. It is literally that simple. And you just put that into your calculator and you'll get what you're looking for. Now, one important thing to note. If your r squared value, I'll try to draw a little example of this. Oh, there goes my lid again. Excuse me for a moment. I'm going to collect the lid for this pen. Where did you... Yep. Nope, you're not there. There you are. I think I'll edit this bit out. So, I'm back. Let's imagine you have, again, x and y. Let's say you have data points here, 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 and here. And let's say that your line goes dead through every single one of those data points. There is no error between your line and the data points. You would have, in this case, an r-squared value of 1. 1 exactly. You could even put 1.000 on there if you like. It is exactly equal to 1. R squared can never be greater than 1, because an r squared value of 1 means that your line perfectly fits your data, or that your equation perfectly predicts what your y value will be based on your x value. You give your equation for that line any x value and it would perfectly predict what the y value would be. Now, alternatively, if, let's say you had just a bunch of random data points. Yeah, you can't draw a single line through it. Let's say you have a line like that. If you got an r-squared value of 0, there is no correlation between your x value and your y values. It is a random distribution, completely random. So, if you want your data to fit a line well, then you want your r-squared value to be as close to 1 as possible. And the lower your r-squared value, the less well your data set fits the line you've drawn. Now, for the record, if, let's say you have a data set doing this, and you draw a line like that, the r-squared value for that line will not be 1, because it does not match the data correctly. Of course, your calculator will try to get you a line which has an r-squared value as close to 1 as possible. But that might have an r-squared value of, let's say, 0.7. Because in here and here, at those 2 points, that line's is a pretty good guess for what those data points would be. Not so much there and there. So the r-squared is a measure of how well is your line matching the data you've got. Now, one very important thing. R-squared will always be between 0 and 1. Your r value can be negative. Line that's there. Draw a line through that. So you might have an r value for this of negative, let's say, 0.98. So even though it's negative, if you square that, you'll get a positive answer, and it's going to be pretty close to 1. So you've actually got a strong linear correlation there. All that negative sign means that it's a negative correlation. But because that is close to 1, or close to negative 1, I should say, or in magnitude it is close to 1, or if you square that it is close to 1, you can call that a strong correlation. So, looking back at my notes, what have we got? Correlation and causation. Okay. You may have heard the expression that correlation does not automatically mean causation. So, for example, if you are watching the footy and you have a sandwich, and as your favourite player is going for a mark, you take a bite of your sandwich, and the player makes a mark. Just because those two things happen at the same time does not mean that every time you take a sandwich, that causes your favourite player to take a mark. Okay? That sounds ridiculous, but there are some cases where it is not so obvious that the two things which seem related are not actually related. Yeah, that's just a side note. So just because there is a correlation, you have to, depending on what sort of data you're looking at, that doesn't necessarily mean that one is causing the other. It's kind of hard to think of an example off the top of my head of when it looks like it is that case, but you can think of you can make up any number of stupid examples of correlation does not equal causation. So, for example, let's say every time I press the on button on the TV, my wife yells at me. Now, that could well be because she's fed up with me watching TV, or more realistically, playing Xbox. But that doesn't. But if every time she yells at me, or every time I turn the TV on, she yells at me, she could be yelling at me for a different reason, and it may just be a complete coincidence that I turned on the TV at that same time. Anyway, point is, correlation does not always equal causation, even though sometimes it may look that way. Okay, next topic. What do we got? Chapter 4. Least squares regression line and coefficient of that line. Least squares regression and correlation coefficients. That is mostly how to do it on a CAS. In fact, Chapter 4 and Chapter 5 are almost exclusively done on the CAS, and for that reason I'm going to be using my computer for this. And Chapter 6, again, could most easily be demonstrated on a computer or a CAS. I'll be using my computer. So, I'm going to switch from the camera to my computer. Welcome to my computer. It is very old, from the year 2007, into 2007, and it runs on XP. So, forgive me if the software looks a little bit ancient, but I still think it's faster than your CAS, and definitely a lot more user-friendly. But, besides the point. So, looking at the Chapter 4, we're talking about least squares regression line and coefficients of correlation, and also how to do it on a CAS. So, let's suppose we have two variables. So let's imagine that, what's a good example to use? Let's suppose you have perhaps, let's say, a car traveling in a straight line, and let's consider the distance it's covering. So we'll call our x variable time, and we'll call our y variable distance. So we'll start off with time at 0 seconds, and distance at 0 seconds, and we'll consider time at 1 second, 2, 3, 4, 5, 6, 7, 8, 9. We'll leave it at 9, that's 10 data points. The distance, let's say the car's traveling along the freeway at a constant speed, so we'll do this in meters. So let's say 25, 49, just making data points up here at the moment, 101, 128, let's say 160, 179, let's say 199, and 220. Why not? So, on your CAS, you would have a spreadsheet that would look similar to this, and in the top you would write something for your first variable, something for your second variable. You would then have a gap, then you'd have a very continuous series of empty cells, and you would put a bunch of numbers into them, similar to this. Now, you can call this and this whatever you like. You can call it x and y. In this case, we have time and distance, so you can call it t and d. You can call it anything you like, as long as you remember what it is. Yep, thanks, computer. For the record, there are no USBs plugged into my computer. It is old. So, time and distance. Now, on your CAS, what you would, to get this into a graph, there are a few ways you can do it as a plot, but the way which I think is easiest, first you press Control, then you press the letter I, and that'll bring up a menu, and from there you should be able to select plot your data. And I believe I think it's like the fourth option in the list. That's the method I would recommend, Control I. So that's why I've written CTRL plus I, or as I like to say, Catarl. Now, in Excel, you would go to Insert, and you go to your graphs, and pick a scatter plot, something like that. Okay. Now, if you're using a newer version of Excel, where you find this sort of stuff is a little bit different, but the principle is the same. So let's say our series name is, let's say, actually, we won't give a name, but the x values, this will be our time, so we'll select these, and our y values will be distance, so we'll select these. As you can see, we've got a nice line going up there. Now, on your CAS, you would usually get a bunch of data points just scattered kind of randomly. You would then, actually, to demonstrate this better, I will add some titles. So let's call this time, and let's call the vertical axis, we'll call that distance. Okay, you would scroll your cursor on your CAS over to where it says time. Sorry, where it's got a spot to put in there, and you would select time, or whatever you've called your x values. Then you'd scroll over here and you'd select distance, or you'd select whatever you want for your vertical axis, in this case distance, and then all your data points should align something like this. If, presumably, assuming you've got this particular set of numbers that I've got here. Just going to check to see if this is still recording. Looks like it. Okay. Now, on your CAS, what you can do, you can go menu, and then I believe it is it's either statistics and analysis. So I think it's analysis, and I think it's the 6th option, could be the 4th. There's something like that. Then I'll bring up another menu, and in there you want to go regression. I believe that's the 4th option. And then you'll either want to pick one, you'll either want to pick the first or the second option. It'll be something like y equals mx plus c. 1 or 2. So if you're trying to get a line of best fit, that's the series of things, or series of buttons you want to press and the menus you want to navigate to bring up a trend line on here. Now in Excel it's a little bit different, and if I can remember where it is, it's been some time. Here we go, trend line. So I'll go more trend line options, just to, so we'll say we want to fit a linear trend line, and let's say display equation on chart, display r squared value on chart. Your CAS will do something like this, and it will give you an equation which looks something like this, and it will give you an r squared value. Now, if you put these exact numbers into your CAS, and you do exactly this, and you plot a trend line just like that, you may get slightly different numbers to what I've got here. Don't let that worry you. As long as they're pretty close, so this should be around 25. This should be around 1.3. This should be pretty close to 0.99. Okay? As long as you've got that, then you're doing it right. So that's good. Now, let's switch back to the whiteboard. And welcome back. So, to the whiteboard. Now, I'm going to simplify this equation because I haven't got a calculator next to me. But from the equation we just saw, so we got a bunch of points here, and we drew a line through them. So we had y equals, let's say, 25, roughly, x plus, and then what do we have? 1.3. Okay. Call that 1.3. Now, you may get a question in an exam, or a test, or a SAC, that says something like, how far would this person expect to have traveled after 20 seconds, let's say? Now, remember, your calculator will give you things, or will give you a trend line in terms of y and x. That's always, y is your vertical, x is your horizontal. Remember, what we plotted was time on your vertical and distance on, time on your horizontal and distance on your vertical. It's a very poorly written version of distance. So, if the question is, how far will they have traveled, or use this trend line to determine how far this person will have traveled after 20 seconds, assuming time is in seconds. So, your x value, that is actually time. And your y value is actually distance. So, what we can do, now I would recommend that you open up your Scratchpad or your new thing in your calculator where you can put in equations, stuff like that. But assuming you haven't got a CAS, which, okay, you should, but if you were to do it by paper, now, okay, well, in reality, these numbers will have a bunch of decimals, so you do it on a calculator. But let's say, so you have y equals 25 times, and let's say if the question is asking after 20 seconds instead of x, you put in 20. And then the rest of the equation is still the same, still plus 1.3. So then y, now you chuck it into a calculator and that'll give you an answer. I'll do it manually here by hand. 25 times 20, I believe that is 500 plus 1.3. So therefore, sorry, I have to sneeze. That would be 500 and 1.3 would be your answer, using these numbers, assuming that's the equation we got there. So, let's head back to the computer. And we're back to my computer. So, one more thing which I should mention. We know that r squared is equal to 0.9973. I mentioned this earlier on the whiteboard. If you wanted to find just the r value, you would simply take square root of that. Is there a function for square root? Square root that number, which would be that. Just wanted to briefly mention that. Now, what we just did here with this data set and plotting that into a CAS and getting a straight line and getting an equation and getting an r squared value and finding a extrapolating a value or substituting in a value into that equation in order to predict what the next y value is going to be at the different x value. That is going to be very important, very commonly done, most likely very commonly done throughout at least the SAC that you're probably going to be facing pretty soon. For your end of year exam, I would very much expect this to be at least a part of it. Otherwise, they spent a lot of time teaching you something which they don't intend to test, which is not very much like teachers. So, looking at my notes, Chapter 5, Data Transformations, Square, Log, and Reciprocal. So, I'm going to call this x, I'm going to call this y, and now I'm going to call this x, I'm going to call this y. Oops, not enter, there we go. So, now in terms of general shapes of graphs, you may have seen this before, but if you have, I'll get rid of that trend line, that's just throwing us off right now. If you have y equals x squared, so in this case, actually what I'll do, let's see if I can actually give you a trend line. It's, that is squared, polynomial, order 2, equation, yep. Okay, don't worry about that 3e to the minus 13, there's nothing to worry about there. It's just a rounding error, and r squared is 1. So this shape here, that is sort of an x squared shape that you get. So if you ever see your data points and they're suspiciously getting consistently larger, so you see it's starting to go up, because here, that's sort of a straight line, but it doesn't follow the straight line, it keeps, the y values keep getting bigger and bigger. You might think that's an x squared sort of plot. Now, alternatively, if you flip this, so instead of getting bigger and bigger, they get more negative, it might look a little bit more, got that one wrong. just a second, it might look a little bit more like this. So again, this is your x squared. Or rather, in this case, it is negative x squared. So if you see something which is curving down and getting, more and more negative, or more and more positive, that might look like a squared relationship. Now, if I copy this, so then, okay, so squared relationships look like that. What about a log relationship? Well, it ain't going to work for 0, so I'm going to increase these there. Let's say equals log. So if y equals log of x, you would expect it starts to plateau out. So instead of the values getting bigger and bigger, they're increasing by smaller and smaller values. The curve is flattening or plateauing, but it will still go up. You just have to go much further in the x-axis to get it to go up in the y-axis. Can I zoom in on this? Even better. All right, let's make these values. Let's say equals that plus 5. So to highlight this a bit further, okay, I didn't quite do what I wanted, but you can see. Actually, hang on, I'll make that 3, 6, and let's make, okay. So you can see that it starts going up, but then it really flattens out. I mean, here the values are going up really sharply, but here it's much more steady. So if you see a curve like that, you might think log. So log of x. Now, what are logs? I alluded that I'd meant to talk about this earlier, but what's the best way to... Can I show you on the computer? Basically, if you had log of 100, that would be equal to equals 2. Because log really, usually, if it's not specified otherwise, if you see log, you can assume it's log base 10. So what that means is 10 to the power of whatever's in these brackets here. What is that power? So in this case, 10 to the power of 2 equals 100. If this were log of 1,000, then that would equal 3. Actually, hang on. Equals log 1,000, 3. There you go. So, you need to make your x values much, much, much bigger before you start seeing your y values go up. Because you had log of, let's say, 1,100, it's not much bigger than 3. It is bigger, but I mean, you increased your x value by 100, and your y value only went up by, well, 0.04 compared to what it was. So that's a little bit about logs. If that went over your head, don't worry too much about it. Your computer will do most of the work. Important thing about the curve that a log plot makes is it flattens out. It gets more steady. Now, the last type of relationship that we're going to look at is what's called the reciprocal. Or, this is 1 divided by x, or 1 over x. So we'll keep, I'll keep those x values, see what it looks like. Equals, that's divided, equals 1 divided by x. So then we make your y values all the same. Let's change that. 2, 3, 4, 6, 10. Sure, okay. So as you can see, it starts going down really fast and it flattens out. In a sense, this can look similar to a log plot. Now you might think, well, that doesn't look anything like this. Okay, but if I make this negative and then apply that to all of it, then similar shape. Not the same, but there are some similarities there. I'll make that positive again just to make it a little clearer. And just for completion's sake, I'll show you what the log plot looks like if you make everything negative. Yeah, same shape, it's just flipped around the x-axis. And I'll change that back. Alright. So, this is, well, I'll make this positive again. But remember, any of these relationships in terms of whether they're squared or log of x or 1 over x, you can always flip it about the x-axis and it'll still have the same fundamental relationship. It's just been flipped, or there's a negative sign involved. So this shape where it keeps going up faster, or negative keeps going down faster, that could be a squared relationship. If it starts flattening out, it could be a log relationship. Now keep in mind, with a log relationship, if you keep making your x values bigger, your y values will keep getting bigger. Now, 1 over x relationship can look similar to a log relationship. Sorry, a reciprocal can look similar to a log. However, with a reciprocal here, in this case, these values will never go below 0. They'll get very close, but they will never quite get there. With a log, they can go up as high as they like. The reciprocals, they have a limit, or it's actually called an asymptote. But now that can be very difficult to see in a plot when you just have a bunch of data points lying around, because I mean, for all you know, the data points will go below 0 if you didn't know there was a rule governing them. But again, similarities. In the textbook I was looking at, they actually told you what the relationship was, and they just wanted you to do that to the data. So, what we'll do, let's have a look. Let's go through some examples. I'll give you some data points, and then I'll show you what we can do with it. So, let's say we've got the x values there. Let's say 1, 2, 4, 6, 9, 13, 17, 21, 25, 26, and 33. Why not? So, this looks roughly squared, right? Now, if you were to try to draw a straight line through it, and to demonstrate, I will show you this. So let's say linear trend line doesn't it's okay, but it doesn't really explain this area here or that area there very well. In fact, this area here, all these points are consistently below the line. So if you saw this data, you'd think it isn't a linear relationship that we're looking with. But if we want to fit a linear trend line to it, what can we do? Well, there is something we can do. Turns out, if you plot, in this case, y against x squared, I'll just call it x squared, then you can get somewhere, because then it might look a little different. We'll just move this over to the side a bit. Yep, okay. So we have our x values here. Let's say that we want to get them squared. So in Excel, I select that, and I use Shift-6 for that little funny hat symbol, 2 for squared, enter, and of course 0 squared 0, double click this little thing here, and that does that. Now, if you are using a CAS, what you will do instead, it'll look like this, and you'll call this, you can call this whatever you like. You can call it X, you can call that Y, again, you can call it that, you can call it that. It doesn't matter, as long as you know which one is your explanatory variable and which one is your response variable, or which one is going to be on your horizontal axis, which one is going to be on your vertical axis. Now, to get this, all these numbers here, your question will likely give you all these numbers highlighted here. It will not give you these numbers. So what you do in your CAS, you put these numbers in, these numbers, then in this cell, you would write something like equals. Then you might say equals x. Now this x is because you call this x. then you would say squared, and you would press enter. Now I might give you a little dialog box or a pop-up and tell that you're talking about the variable, and hopefully, now Excel doesn't like that, what I've done, but hopefully you would get all these numbers here. Okay, so you might have to fiddle with your CAS around for that a little bit, but just keep giving it a shot. So remember, it's in this cell above where the actual data goes. You write equals, then you would put in whatever you've called this variable here, then you would say squared. Now, when you do that, you may find that what you've called this disappears. Maybe. I've had a lot of issues of the CAS just saying, I'm going to change what that's called. I'm going to forget what you told me to call that. So when you go to plot your data, you may find you don't have your x squared thing that you can call here. Now in Excel, it's a little bit easier because, I mean, well, it's a better user interface, dare I say. So let's say that instead of x, we're calling it x squared. And now, again, it's not a perfect fit, but hey, it looks a lot better. And in my defense, I made up these numbers on the spot, so I think I'm doing okay. Okay, and I'm back. It appears that my capturing software, at least the version I've got, only does 15 minutes at a time. So I'll have to retrace my steps and walk you through what I've done. So what we've done, we had our time and speed data that we got. Then we squared time, and we've plotted time squared on the x-axis and speed on the y-axis, or the vertical axis. Then we plot a linear trend line through that, and we see that based on the fact that the r-squared value is quite close to 1, that it seems that this is a good fit. Or in other words, that a squared relationship is suitable, and if you plot it on time squared, then that becomes a linear relationship. And we get this equation here. Y equals 0.3824x plus 2.3028. Now, if you do this on your CAS, you may get slightly different numbers, but they should be pretty similar. Don't worry if they're a little bit different. It's just the way that that your CAS and Excel do things a little bit differently. It should be very similar. Now, suppose you have a question in your test that said, here's your data, linearize the data, so you might plot it against time squared, and you might get this, so you think, great. Then it says, write down the equation of the line of best fit and the r-squared value, so you'd write down this in your test. Then they might, and the last part of the question might be, based on this, what speed would you expect this person to be traveling at when time is equal to 12 seconds? Now, I've already done this, so I'll walk you through it again. Now that's your equation there. So now remember, what we plotted on the vertical axis, or the y-axis, was speed, s. So this y here is actually your speed, s, from up here. Your x here, from this equation, is actually t squared. So remember, the question said what's the speed at 12 seconds, but in this equation, do not put in 12, because x is not time, x is time squared. So instead, for the x value, you would put in 12 squared, because time squared, when time is 12 squared, so that'll be 144. Or x here is equal to 144. So then you'd write down something like this, y equals 0.38 times 144 plus 2.30, and you get an answer. Rather, you'd put that into your CAS and you would get an answer. Then, so your answer to the question that they asked, what is the speed at time equals 12, would be 57.02. And if you put that into here, it should be right on that line there, because we use the equation of that line to work out where that data point should be. So that is that. Now, here's another data set I prepared earlier, and I hate to admit it, but I actually made a bit of a mistake the first time I did it. But I fixed it now, thanks to being able to cheat by looking at the graph. That's besides the point. So here is another data set. Let's say they would give you this to you in a question, and here is that plotted on a standard XY set axes. Now I've called them X and Y because I can't think of a good realistic example of what this could apply to, but if you rotate your head to the right by 90 degrees, it would look like that the data points here are starting to plateau out a little bit. Honestly, you could also plot this as an x squared, in all honesty, but let's suppose that the question tells you plot the y data values as log of y instead of y. So let's call this log y. And then in here on your CAS you would write equals log open bracket, and you'd write y because that's what you've called that there, close bracket, and then you press enter on your CAS. Of course in Excel it doesn't work out so well. So on Excel, it's simply a bit like that. And you would do this. And then instead of x and y, you would be plotting x and log y. So let's go select our data, edit, x values, y values. For our y-axis, we'll plot this. And what do you know? It looks kind of like a straight line. Not perfect, but I mean, well, it shouldn't really be perfect. But nonetheless, that looks very much more like a straight line compared to what we had earlier. So you would then follow this layout here and get a trend line. You would get an equation and an r-squared value. And it would be something like this. Now, so your equation would be y equals 0.076x plus 0.8995. Now remember, similar to the previous case here where x was not equal to time, but x was equal to time squared because we plotted time squared on the x-axis. For the y-axis, we didn't plot y, we plotted log y. So y is actually equal to log y, and x, in this case, is actually still equal to x. So that's fine. Now, let's say, so we know that y equals, and let's suppose the question is saying, what would you expect the y value to be when x is 20? Now, based on this equation here, or here, you can put x equals 20 right into this equation because we plotted the x value, so the x data points onto the horizontal axis. So that's fine. So we can do y equals 0.076 times 20 plus 0.8995. And then if you do that, you would get something like, well, actually, you should get exactly this, that number. So you would expect y, log of y at x equals 20 to be 2.4195. And if you were to put that point onto your plot here, it should go exactly where the line is. Now, but the question didn't ask you what is the log y value when x is 20, it asked you what is the y value when x is equal to 20. So, I'm just going to make sure I'm still recording. Looks good. So we know that log y equals 2.4195. And what that really means is that 10 power of 2.4195 equals y. Because remember, log by default is base 10, and it's 10 to the power of whatever the answer is what's in that bit there, in this case y. So if you do 10 to the power of 2.4195, I believe on your CAS it's that little little funny triangle symbol there. It's tucked away in the left side of your keypad. I think it's a very small button, but actually no, it's a pretty big button, I think. You can find it better than me. So you would put this into your calculator, and you would get that. So let's have a look. Let's put 2.7 was it 24 in there, and let's then say equals log that. Of course, Well, we did it the other way around, so we know that should work. But if the question was, what is the y value when x is 20, your answer would be 262.724, to however many decimal places they ask for. Your answer would not be 2.4195. Now, I guess what I'm really trying to hammer home with all these examples is when you get an equation in this form, don't blindly put in your x and y values into this equation, even though this equation is in y and x's, because you always want to put in the terms of what you plotted your data with. So y is not simply y is log of y here. In the previous example, x is not x is time squared. Sorry, x is not time, x is time squared, because we plotted time squared. So there's that. I'm going to pause the recording there. I'm going to give you one more example of this sort of stuff. Okay, so we were just looking at linearizing data using the log function. We'll do one more example. We'll go back to the first one we made of reciprocal data. So we've got this data set here that I made earlier, and now when I was in year 11 math, we had our self-professed ladies' man. We'll call him Billy. And as our teacher said, here we have an asymptote. The values get very close to zero, but never quite get to zero. And he likened this to our resident ladies' man to distance to girls. He can get very close, but he can never touch. I'm not making this up. Enough about years ago, high school stories. Let's suppose we have this data set, and let's pretend we have this particular circumstance. So our x-axis will be, this will be time. Because over time, Billy can get closer and closer to the girls, but of course, he can never touch. Distance to girls. Super classy right now. But I'm sure the ridiculousness of this whole situation means you will not forget what I'm talking about. So, clearly this is not a linear relationship, but what if we did 1 divided by time? Now, in your CAS, it may complain if you put in a mathematical operator for what you're trying to call it. So let's just call it tdiv. Well, let's just call it tdiv. So what it actually is going to be equals 1 divided by time. And of course Excel doesn't like that. But what we're going to do, or what I'm going to do rather, 1 divided by that. Take that all the way down. And of course this is going to be a very, very good fit, because it's exactly the same way that I found what the y value should be. So there you have it. Perfect linear relationship. This isn't time, this is 1 divided by time. And of course you can't divide by 0, because then you get infinity. So let's then fit a trend line to this. Trend line. More trend line options. Linear equation, r squared value. And of course the r squared is 1, but we just have y equals x. That's a little bit boring. Tell you what. I'm going to make this a little more interesting. Let's suppose we have 1, 0.48, 0.35, 0.22, 0.15, 0.12, 0.05, 0.048, 0.041, and 0.035. Okay. So, our equation's a little more realistic now that I modified data set. So it's a bit of variation. It's not a perfect representation, but pretty good. So our equation is y equals 0.9974x minus 0.0039. Now, suppose the question that they ask is, how close will our good friend Billy be to the girls at time 50? Don't know. But we do have an equation here. Now remember, y is equal to distance to girls, and x is equal to 1 divided by time. So, time is 50, but we're not going to put in 50 into our equation here. We're going to put in 1 over 50. So 1 divided by 50 should be 0.02. So then you'd write into your calculator 0.9974 times, and your x value here, remember it's 1 over time, so that's this one here, 0.02 minus 0.0039. So I'm going to say, I'm going to copy that. Nope, fluff that one. Equals, paste, false. No, don't do that to me. Minus 0.0039. Gonna correct that. 0039. Okay, and there's your value. So then if we said that the y value should be this, then if we were to extend our data set to include what we just calculated, it should be right on the line. And okay, it's very difficult to see because we're right in this region here, but of course it should be. So we'll just undo that. Okay, so that's about summarizes the different sorts of things you can do with modifying your data. Okay, and lastly we're going to be talking about Chapter 6. Now, Chapter 6 is mostly about time series data, and fundamentally this is not really anything new compared to what we've done in the previous 2 chapters. The only real difference or specification is that on your x-axis you have time. That's pretty much it. But there are a few things which are new in this chapter, which are not necessarily for time. So let's suppose that we have a data set, and I'm going to use one of the examples from the textbook. So let's say we have days. Actually, I'll start this more on the left side of the board. So, days, and this will be temperature. Temp. I'm just doing a great job here. Okay, now our days are going to be Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. And let's say that we're looking at a maximum temperature. So let's say that here we had a maximum of 30, maximum of 27, maximum of 34, maximum of, let's say, cooling down 21, and 18, then let's say 19, and perhaps a maximum of 24. Perhaps not too unrealistic for what Melbourne weather can be like. So, if you were to plot this, so let's say this is your day, this is your temperature, you might have it look kind of like this. It's all very kind of a zigzaggy sort of thing. Which makes you think that, well, hang on, it looks like that the average temperature is jumping all over the place. Sorry, the maximum temperature is jumping all over the place. And in truth, it kind of is. But, and that might because it's jumping all over the place, it might be harder to see what an overall trend is. Because remember, I mean, you can have like one very hot day in the midst of some more moderate days, but you wouldn't conclude that the whole week has been really hot just because there's one spike in the graph. So what we're going to do now will sort of compensate for that. So what we're going to be doing is what's called, we're going to do 3 mean smoothing, 5 mean smoothing, and 2 and 4 mean smoothing with centering. So you may find a question that says, what is the, if they may, so if you were, so 3 mean smoothing, what it really means is they want you to find the average of 3 days, or sorry, 3 data points. In this case, it's days. So let's say they want to get the 3 mean average of Thursday. So you would look at the data point, one to the left and one to the right of Thursday. So that's 3 data points, with Thursday the one in the middle. So we're caring about Thursday. What's the 3 mean average for Thursday? So we take these points. So 34, you do this in a CAS most likely, plus 21 plus 18 divided by 3. So then what's that? 21, 18, 9, 39, 73 divided by 3. That's equal to what? 20, not 25, 24.3 recurring, I think. Let me have a good think about that. Yeah, sounds about right. So your average, your 3 mean average centered on Thursday would be 24.3, or 24.3 recurring, or 24 1/3. So that's your 3 mean average. Your 5 mean average is calculated very similarly. So say you want to get the 5 mean average for Friday. So we need to look at with 5 data points with Friday right in the middle. So in that case, it would be Wednesday, Thursday, Friday, Saturday, and Sunday. So then you do 34 plus 21 plus 18 plus 19 plus 24. And you divide that all by 5. Alternatively, well, actually, and then in a CAS, you might just put that first line into calculator, get your answer, and divide your answer by 5. You can do that. I'm not going to spend all this time working that out. I'm sure you can plug into a calculator and get an answer. But that's a 5 mean smoothing. So if you were to so let's say if you wanted to do 5 mean smoothing, you might have data points for Wednesday, or it's actually Monday, Tuesday, Wednesday, Thursday, Friday. Well, that might be X. We'll call it X. Then you have one for Tuesday, Wednesday, Thursday, Friday, Saturday. So that'll be centered for Thursday. We'll call that Y. Then you'd have Wednesday, Thursday, Friday, Saturday, Sunday. And then we'll call that Z. So then you would have your plot of days, and you'd have your temperature, but you only have 3 data points. And presumably, because you've averaged them all, or you've done averages to get these, your 5 mean smooth graph will be a lot smoother than the original sort of a jagged shape that we had earlier. No idea if that's reasonable representation or not. But that's how you'd calculate the 5 mean smoothing for that. Now, 2 and 4 mean smoothing. Unfortunately, this is just it's a bit more work for, dare I say, not a whole lot more gain. So let's say you wanted to do 2 mean smoothing with centering for Tuesday. So you would take the average of that point and the average of Monday and Tuesday and the average of Tuesday and Wednesday. So that'll be 30 plus 27 over 2. That's 7. And 27 plus 34 over 2. So that'd give you 28.5, and this one would give you 30.5. And then, to get your final answer, you'd want to get the average of these two numbers. So that would be 28.5 plus 30.5 divided by 2. What do we got there? That's 29.59 over 2. 59 over 2, which is equal to 29.5. Yeah, that makes sense. Cool. So your answer to 2 mean smoothing with centering for Tuesday would be 29.5. Now, 4 mean smoothing with centering is a similar concept. Let's say you want to do 4 mean smoothing. Well, you wouldn't want to do it, but let's say that your test or your exam or your SAC asks you to do 4 mean smoothing with centering for, let's say, Wednesday here. You would, so 4 mean smoothing, you can't put Wednesday right in the middle. So what you do, you put it as close to the middle as you can. Now there's 2 possible ways to do that. You can consider Monday, Tuesday, Wednesday, Thursday, or you can consider Tuesday, Wednesday, Thursday, Friday. Which one are we doing it for? I totally forgot. For Wednesday, yeah, because Wednesday's got 2 on the left and 1 on the right, and then 1 on the left and 2 on the right. So then you would do 30 plus 27 plus 34 plus 21 divided by 4. Now let's say it's equal to x. I mean, you can chuck it into a calculator and work out what that is, but I'm not going to do that by hand now. And then you do 27 plus 34 plus 21 plus 18 divided by 4 to get your mean average of, let's say it's y. And then you would get your average of x and y. And whatever that is, that would be your answer. Sorry, I shouldn't. That would be your answer. I don't know what that is, but you can use a calculator to work that out. And that would be, so your answer here would be and if the question is 4 mean smoothing with centering for Wednesday. So you got Wednesday in the middle in 2 different versions, Monday, Tuesday, Wednesday, Thursday, and Tuesday, Wednesday, Thursday, Friday. You've done averages of those 2, and you've got your 2 averages there, and you average those together. That will be that. Now, what else have we got? Moving medians. Okay, this is a graphical thing, so I'm going to... Fortunately, this is only graphical, so there's no real formulas you need to memorize for anything like this or anything like that, which is nice. Okay, now remember, your median is your middle value. So we'll call that x, and we'll call this y. Let's say we have a bunch of data points. Let's say here, 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 and let's put one here, and let's say another one there. Okay. Now, if the question is saying put on the graph the, what do they call it? The median smoothing, how do they word it? The moving median for sets of 3 values. I'm sure they'll probably word it differently than that. You look at 3 values at a time, and you find the middle x value and the middle y value for that set of 3. So let's, I'm going to get real colorful here. Let's look at these first 3 values first. Consider only the x values here. Maybe that's a 1, a 2, and a 3. So this point there, that's sort of in line with your median x value. Now, let's look at the y values. Maybe that's a 2 on your y-axis. Maybe that's a 2.5, maybe that's a 3. But this point here is your median value in terms of y values. So, forget the dotted lines for a moment. Considering these three, your median value would be there. Just going to get rid of that circle. So that's your first median value considering 3 at a time. You would then do this for the rest of them. So let's consider these 3 values here. So obviously this is your median value for x, 1, 2, 3. So, and again, that point there is your median y value. So y and x, so you put a point there. 1, 2, 3. This one here, that point there, that's your second x value of the 3. It's also your second y value of the 3. So this point will also actually be a median value. Now, 1, 2, 3, same thing again. The second x value has the middle value, and sorry, the second point has the middle x value, and the second point has the middle y value. So I'll have that one again. Now, 1, 2, 3, that's your median x value. Then in terms of 1, 2, and 3, this is your median y value. Again, 1, 2, 3, the last one, that's your median x. But 1, 2, 3, that's your median y. And you can do this for sets of 5 data points, sets of 4. Well, you could do it for sets of 4, but then you'd be kind of averaging a bunch of stuff together. But compared to that sort of kind of a jaggedy black, if you were to connect all the black dots together, you're kind of a jagged line. But if you connect all the red dots together, it's, for the most part, a fair bit smoother. I mean, it does change down here, but it's sort of one smooth curve rather than a bunch of jagged sections fused together. Okay, moving medians. Now, the second last thing I'm going to be talking about is seasonal indices. Now, full disclosure, I'd actually never heard of seasonal indices before I looked at this textbook, but in my defense, I didn't do anything like commerce or economics, so that's my excuse. But nonetheless, mathematically, it does make a fair bit of sense. Now, imagine that you run a store that sells surfboards. You're going to sell a lot more of them in summertime than you are in wintertime. At least I would expect that to be the case. So, if you look at your sales figures across a year, let's say, let's call it summer, that's a U and an M, by the way. Then what do we get? Autumn, then we get winter, and then we get spring. Okay, forget the fact that I'm struggling to write right now. So let's say in summer we make $100,000 worth of sales. I'm just going to call it 100. This is all to the nearest thousand. Rounded up, sorry, this is all in thousands of dollars. So 100. Autumn, your sales slow down a fair bit. So let's say like 50. Winter, let's say 15. Then spring, things pick up again. Maybe up to 70. So 100 grand in summer, 50 grand in autumn, 15 grand in winter, 70 grand in spring. Now, this will be your revenue, or the amount of money that you bring in from sales. Now, your seasonal index, or indices for plural. Now, if your sales are doing really well, then your seasonal index should be above 1. If it's a typically slow sale period, your seasonal index would be below 1. But it's important to remember that the average of your seasonal indexes should be, it has to be equal to 1. So let's say that in summer you have a seasonal index of 1.7. In autumn, perhaps you have a seasonal index of 0.8. In winter, seasonal index of 0.5. And if I'm doing my math correctly, yeah, 8, 5, 5, 5. Let's say in spring, yeah, just want to make sure, yep, let's say I have a seasonal index of 1. Now, you should be able, now because we only have 4 seasons in a year, so we only have 4 seasonal indexes that we're considering. If you add all these together, you can chuck this into a calculator if you don't believe me, or maybe to prove me wrong, I hope not. That should equal to 4. And because you added 4 numbers together, 4 divided by 4 equals 1. In other words, your average of your seasonal indexes is 1. 1, 1.5, 2.3, 4.0. Beautiful. So if you ever get a question, and let's say that it's missing this number here, and they say, what's the seasonal index for winter? You could add up all these together. So 1.7 plus 0.8 plus 1.0 equals 3.5. And you go, okay, that should be equal to 4. So if you then do 4 minus 3.5, that will be equal to 0.5, and you know you should have 0.5 as your seasonal index there. Now, that is your actual amount, or that's the actual amount of revenue you made. If you want to seasonalize your revenue, in this case it's revenue, but if you want to seasonalize, what you do, you take your actual value, I'm just going to call it actual, and you divide it by your seasonal index. And that will give you a seasonalized or deseasonalized? Deseasonalized. I gotta check this. That will give you a deseasonalized value. Okay? Deseasonalized. Word of the day. Similar to its cousin, reseasonalized, which we'll get to. Now, I'm going to call that DV, because I don't want to write that word all over again. If you know what the deseasonalized value is, actually, I'm going to write this up in the top. If you know what your deseasonalized value is, you can then, and you want to work out your actual value, or in this case your revenue, you can multiply it by your seasonal index. Seasonal index. SI for seasonal index equals actual. Okay, so if you wanted to, let's say, so summer you made 100 grand. That sounds great. But you know you're going to make a lot of money in summer. So try to work out what it is a sort of more accurate representation of how well did you actually do. So if you wanted to get the deseasonalized value for summer, you would do 100, that's your actual, divided by 1.7. And to this point, I really wish I had a calculator because I'm not going to do that in my head. But very roughly, it should be around 60. If that was 1.5, then that would be 66. So I'm going to say it's around 60. And if that were 2, that would be 50. So it's around 60. Now, if you were simply to plot your actual against your seasons, you might get 100, 50, 15, and 70. A little bit bigger. So it would go down and then up. That's really not a very healthy business model. If you use deseasonalised values, it should be much smoother, much less. All the peaks should be, all the sharp spikes should be softened in a sense. So that's how you would get a deseasonalised value. Now, if you knew what your deseasonalised value was, so let's say we know that the deseasonalised value in winter is, let's say, we'll change it up a bit. Let's say it's 40. Then your actual, now for winter, would be 40 times your seasonal index, which is 0.5, which is equal to 20. Now I know it was 15, but I'm changing the number just to mix things up a little. Boy, I did not write in straight lines. That is a curve if ever I saw one. Okay. Time for me to look at my notes and what else there is in the syllabus. Alright. As I mentioned earlier, if your seasonal index is above 1, means that this is the season where you expect to do well. If your seasonal index is below 1, it suggests that you would expect to not make as much at that particular time. So, now let's move. Now, we did plenty of stuff on the computer already with plotting data sets and getting lines of best fit and linear regression and getting an equation and extrapolating information and all that. The important thing, the only new thing I'm going to tell you about that now, let's suppose you have deseasonalised values here, and this here will be time. So you have a bunch of data points doing something kind of like this, and you have a straight line. And let's say you know what the equation of that line is. Let's say it's y equals, I don't know, 3x plus 1. Alright? Now, y is your deseasonalised value, x is your time. And so let's say that here time is, I don't know, 10. And the question is, what is your actual value at time equal to, let's say, 15? Yep, it's all fitting in the camera. So, you take your equation, and we know that x is time, so in this case we can plug t equals 15 straight into that equation. So, y equals 3 times 15 plus 1, which if you chuck into your calculator will give you an answer, but 3 times 15 will give you 45 plus 1. That will give you 46. So, your deseasonalised value at time is 15 is 46. But the question isn't asking what's your deseasonalised value, it's asking what is your actual value. So, in order to do this, pardon me, we need to take the... Alright, I've got to read my notes just so I don't get this wrong. Deseasonalised value equals... Right. In order to get the actual value, we need to multiply the deseasonalised... Because remember, y is your deseasonalised value. So we need to multiply this by the seasonal index. Now let's suppose that the seasonal index at t equals 15 equals, I don't know, let's say, just to make this easy on me, 46, let's divide it conveniently by, can you do it by thirds, quarters? Not by quarters. Threes, no. Alright. Let's say it's a seasonal index here is 0.5. So, You would then take your deseasonalised value times your seasonal index equal your actual value. Deseasonalised value is y, so that's 46 times 0.5, which is basically just dividing that by 2 or halving it, which will give you 23. So 23 would be your actual value at t equals 15. Alrighty then. So yeah, the take home from this is that when you plot your data, get an equation, plug your values into it, all fine. You make sure that t, and if you've got t here, then it's actually you've plotted against t. If not, if that's, for example, where t squared, then you would want to put in a squared value of t into your y equals x equation. In this case, that's not what we're doing. But then any output you get will be whatever you've plotted here, which in this case is a deseasonalized value. So you want to re-seasonalize that, or to get that back to an actual value. And somewhere in the question, or there'll be some information which will give you the seasonal index. Multiply a deseasonalized value by your seasonal index, and in this case, with 46.5, you'll get 23. So that about brings me to the end of everything I want to talk through. Hopefully this has been useful. I understand it's a lot of information. Give me some feedback. I imagine make it shorter and briefer will be the #1 recommendation. And boy, I would like to do that. But sometimes I just keep going and we end up here where I start rambling. Anyway, that's about all for now. Thank you for watching. I hope you got something useful out of it. Good luck with all your future tests, SACs, and of course your final year exam. Thank you. Goodbye.